So now we're talking about training a network. So once the data has been loaded, an optimizer and error function is needed for the training. So we can call torch.optim that will give us different optimizers. So we have error functions also in torch.nn. We have so we can use this as layers. For example, if we want to perform multi-class classification, we could use things like optimizer by stochastic gradient descent with torch.optim.sgd, cross entropy as torch.nn.cross entropy loss, and it gets us to something like this. So we have here the listing for LeNet 5 training. So basically we have the setup which says 10 epochs, batch size of 64 samples, learning rate of 0.01, momentum of 0.9. Then we have the MNIST dataset that we will load from that path. We will create a data loader to get the data in batches. We create LeNet 5 model, we train it, and then we are able to optimize it. So the train is not making the training. In fact, the train is switching to training mode. So we need to do this. So we are now in training mode, and then we do the optimization with SGD. So train.optim.sgd with the parameters, learning rate, momentum, etc. And then we are able to evaluate the cross entropy loss by using that function. And then we are doing this over several epochs. So I epochs giving us the iterator for the epoch from 1 to NB epochs. Likewise, for the batches, we are getting through all the element of all the batches of that was given that by our data loader. So we get the batch, then we reset the gradient to 0, then we compute the predictions with getting us y hat, then we compute the difference, the criterion between y hat and y. Then we are doing backward propagation to get the graph, and we perform a step here. So we do the backward and then a step to optimize the values of our network. It is possible to back up a network via a state directory with the function torch.save. So with torch.save, we are taking up the state, which is given by state dict from a model into file. In the same way, we are able to reload it. So we are taking back the state, loading it from a file, and get it instantiated as a model. So that's nice to use predefined train network, or even just doing checkpointing with our network. And it's wise also to load the network with a destination to first make use. It is on the CPU, so it's good to map this in with a destination first to be sure that it is at the right place. More details in that link. The subpackage Torch Vision implements also several models useful for computer vision tasks. We can load with pre-trained weights, train on the huge ImageNet natural image dataset. For example, we can load a ResNet 18 with pre-trained weights on the ImageNet with that function. So basically building up the ResNet 18 model, but setting the flag pre-train as true. And then we can also access to network parameters with the layer name with the method name parameters. So this is interesting to analyze the network and use it in making possibly accesses by name also. So if we want to modify the network, we can just change the name of the layer with a function that we can call nouvelle couche, for example. It will give us, will allow us to modify. So we can just say model that name of the layer, and we have this name that way, and we can reassign that layer of that name into something else. And we are also able to freeze some layers directly by setting the requires grad to false by using accessing to the layer according to its name. One thing that is important is that if you freeze layers, it is important to only give the parameters to be optimized to the optimizer. We should not give it more than this. So we possibly need to filter out all the parameters that are not requiring gradients, that are not known to be requiring the gradient because the optimizer will not work on them. We should not look at them.